Hello, AP students. This is Mrs. Gerhart, and this video will address hybridization. If we take methane as our teaching example, we know that methane assumes a tetrahedral geometry. There are 4 single bonds between the carbon and the hydrogen. So 4 areas of electrons will give us this tetrahedral geometry with equal length and bond energy for all of these. However, that doesn't quite match our understanding of where the electrons are in carbon. So we know our electron configuration has the 1s, 2s, and then 2 solo electrons with the same spin in 2 orbitals of the 2p. That doesn't quite match how we get this geometry. Okay, what do I mean by that? Well, if this is so, we know carbon is found on an XY Z axis, the nuclei, and then we have an S and then 2 of the P, and let's just say that they're on the X and the Y, well then shouldn't the electron sharing be on 90-degree angles? How do we get this 109.5? The theory is this, that the orbitals get hybridized. That carbon's electrons will first promote one of the paired to then have 4 solo electrons, but then we blend the 1 s orbital and then 3 of the p to get 4 orbitals of equal energy. That'll be slightly lower than the 2p, but then higher than what the 2s would be. Let me show you a nice computer imaging of this. All right, so what we see in the middle of the screen is what I started to show you. And then we understand, or in our humanness, we say that the paired electron got promoted. And now we have these 4 solo valence electrons that can accept another from each hydrogen to form a single bond. Okay, but what we predict is this idea that the S and the 3 Ps, because we end up with 4 positions of bonding, so that needs to come from 4 blended orbitals, that they create now 4, and it's kind of a morphing, and you'll see in your book, in different textbooks, different computer diagrams, you'll find all kinds of different predictions as to what the math tells us hybridized orbitals look like. But the math says then that these 4 hybridized orbitals will be located in a tetrahedral geometry with a 109.5-ish bond angle between these areas. Now, because we are blending 1s and 3 p's, that is called sp3 hybridized. One of these came from the S and then 3 p's. Okay, now this is out there stuff, and I definitely know it. I definitely know it. So here is kind of a working definition. This, of course, is found in your packet. All right, what we need to be able to do is just connect, truly, truly, truly. And in class, I'll show us something where I'll write on my fingers to help. But what we just have to understand is, okay, if we have our center atom, and it's bonded to 2 other elements, we have 2 areas of electrons. Now, hybridization also applies to non-bonded. Those are going to be in a hybridized orbital. So whatever our electron, the number of areas of electrons, they all get counted. So when we have two areas, that'll be an S and a P. When we have three, the three will come from 1s and 2p, and then 4, 1s and 3p, and so on. So the hybridization directly connects to the number of electrons, which is our electron geometry. We know that our s orbital is going to be at our lowest position of energy, right? Our lowest position of energy. And that we have p orbitals. Now, it depends on the element, but we could also have d available. All right. However many number of electron areas, they came from hybridized orbitals. So if we need two areas of electrons, that will be 1s and 1p. That will be sp hybridized, just 1s and 1p, which is the linear geometry. If we need three areas, that will be 1s and 2p. That'll be sp2 hybridized. Our electron geometry, trigonal planar. If we need four areas, that's where you get the S and then 3p. Where do we go next? Well, we're only going to go beyond tetrahedral electron geometry when we have some d orbitals available on that element. And so how would we get 5? Well, we're always going to start with our lowest energy, 1, 2, 3, 4, and then pull in a d. Now, there's definitely some discomfort with calling this hybridization a hybridization, but until we find data otherwise. So the concern that chemists have is we find evidence and backing for hybridization of these geometries, but we find the trigonal bipyramidal geometry, but it doesn't quite match hybridization with the D. But it's the best we have right now. And then how do we get the octahedral or 6 areas of bonding? Well, it must be sp3d2. So that is just what we have to be able to connect. So as soon as either you can declare the electron geometry, then you know the hybridization, or the number of electron areas, then you know the hybridization. So, for example, if we were asked to give the hybridization on the nitrogen in ammonia, well, that would be nitrogen with 1, 2, 3, 4 areas. We always start with the S, and then we have 3 P's. That gives us 4. So it will be sp3 hybridized. And even though we would call this trigonal pyramidal, our electron geometry is tetrahedral. The hybridization on this nitrogen, a triple bond, remember, counts as 1 area of electrons. So 1, 2, it would just be sp hybridized on each nitrogen. Multiple bonds are shared in non-hybridized orbitals. We don't have to know that for now. We just have to be able to just answer hybridization on a center element or on other elements that might be identified for us. Here are just some sketches of these hybridized orbitals. But again, if you're asked, what is the hybridization on carbon? we need to be able, from the Lewis dot or from the Vesper drawing, be able to conclude how many, what the hybridization is. And remember, single bonds are sigma bonds. So sigma bonds are the hybridized. Here's just showing us what it would be on a carbon in this molecule. And then the carbon here would be just sp hybridized. There are some other images, of course, in your book. Here are just some other little nuggets of information. And here's the kind of thing that we need to be able to answer regarding sigma and pi. But for example, if you were asked for the hybridization on this specific carbon, let's see, we have 1, 2, 3 areas, sp2 hybridized. Okay, as always, please send any concerns my way.